Claro, pero no es limitado. Yo creo que en los 90 sí. Yo creo que en los 90 sí. Pero ya más adelante, yo creo que ahora son Hugo y Lucía. Una vez iba por el parque y Hugo. Y yo creo que por lo menos 10 niños se giraron a ver los dos.
Hello, yes. Vamos a ver. Sí, Leandro, are you ready?
Yes, just a minute.
Yes, whenever you want, we have time. There's no rush.
Yes. You can see my presentation?
Yeah, I can see it. It came out today, the paper, right? Sí, da para verme. Attention, the session, afternoon session is starting. Our next speaker is Leandro Leza from the Federal University of Ceará in Fortaleza. And he's going to speak about a very recent work on brainwaves in cubic gravity. So, Leandro, whenever you're ready, go ahead.
Can you hear me?
Yes.
Good afternoon, everybody. First of all, it's a pleasure to participate in this meeting. Congratulations to your organization for the beautiful event. So, my name is Leandro Lessa, and I am a PhD student at Universidade Federal de Ceará in Brazil. So today we're talking about Brownian's world in cubic gravity. The presentation is based in this paper, and that's an archive. There's a number. My presentation have this 4 points. The first of all, I will talking about it and how to construct to higher curvature theory up to curvature cube interaction and a warped spacetime. And then we apply this and try to looking for the think-brain solution. And then I will discuss about the localization of the tensor mode and the theory, and then I will conclude it. So the first part is the main goal is to construct a high curvature theory, standing up to cubic order with a second order equation of motion for the warped geometry. Warped geometry means 5-dimensional space-time. It's described by a warped metric. So the action we work is given by this equation 1. And of course, this is in 5 dimension. The first term is usually general relativity term. That is the Einstein-Hewitt term. The next one is the quadratic term. That is the term formatted by the construction of the 2 curvature tensor. This term is composed of the 3 possible invariants. You can see the equation 2. The next one is the cubic term, the formatted contraction of the 3 curvature tensors. In this case, you set up the possibility of increase to 8. You can see the set of this invariant in the equation 3. And in this last case, we will denote this 8 invariant by the invariant P. It's a main quantity in this presentation. But it's a curvature tensor or Riemann tensor or heat tensor even have a second derivative of the metric. So the quadratic and cubic term introduce high derivative into the equation of motion. So this made signal instability in this theory, like a ghost. So what you try to answer here is what are you going to do to get around this problem? What you need to make to solve this problem, the high derivatives in the equation of motion. So here you assume two hypotheses to try to solve this problem. The first is based on in this paper by two published, probably some of you know them. They introduced in this paper the cubic gravity, called Einsteinian cubic gravity. For us to assume that for the action one that I introduced previously, the gravitational fluctuation and the linear regime have the same spectrum as the general relativity. That is, the transverse and the MATLAB graviton propagated dynamically on a mass symmetric background. Is important because in this paper then assume that the graviton lives on a mass symmetric background. This simplifies too much the counts. So if you assume that, you can fix it two parameters of the cubic gravity. And the expression for this fixation is given by this equation 5 and 6. This fixation is when you assume 5 dimension. Remarkable, this condition leaded to famous Gauss-Bonnet term for the quadratic term. So this, and the equation is 7. It's important to explain why you don't discard and eliminate this contribution of quadratic term in this analysis, because in 5 dimension, the Gauss-Bonnet, we know it's not more topological term. So you need to consider in this presentation. But even with this condition, in general, the equation of motion due to the cubic interaction have high derivative. So you need to solve this problem yet. So to overcome that, let's first assume this 5-dimensional spacetime described by this warp metric equation 18. The A function is called the Warp factor. So if you assume this geometry, and if you fix another parameter of the cubic gravity, in this case beta 6, equation 9, you can show that the high derivative term in the equation of motion is eliminated. So indeed, assume that the Lagrangian of matter is given by real scale field, we can obtain the following equation of motion, then assume the warp metric and another two assumptions, the two hypotheses I previously said. Note that this two highlighted term here, the purple highlighted, is generated by the Gauss-Bonnet term, the quadratic term. The yellow highlighted is generated by the cubic gravity when you assume the two fixed of the betas. And in the last equation here is the equation of motion of the real scale field. So indeed, we have the equation of motion without a high derivative. So what you do now in the second part and the next part is applying these equations for different contexts of the Brownian rule. So in the second part, we will look for the think-Brownian solutions. Remember that we assume that the scale field lives on the book. So the scale field depends on the extra dimension. So to do this, we assume you use the second order formalism called BPS. Using it, it's possible to rewrite the trivial equation of motion into that first order equation that depends on the choice of the superpotential. Superpotential is near here denoted the W function. And in this case, we will choose a superpotential that is linear in the scale field equation here in 18. Replace this superpotential into the equation 17, you will obtain the potential. In this graph, you can now build the graph. You have the potential as function of the scale potential or scale field, sorry, and you can see that your vacuum structuring here, when you see the minimum, is only evident when you introduce a correction to the high curvature things. Curvature theories. For the superpotential, you can analyze another quantity, such as energy density for the scale field, or how the warped background, warped factor feel the high curvature tensor, and the profile of the on the scale field. Here in the, for example, in the graphic C, we can see the profile of the field, a scale field. You can see that the presence of the king solutions, and the graphic A, you can see the profile of the energy density, and the overall property about this, the quantity, energy density, are the preserved with respect to usually general relativity. And in the last graphic B, the profile of a warped factor characterized a compactified brane. In the first and the last part of this presentation, you will study the propagation of the gravitational fluctuation for this cubic gravity and the quadratic gravity too. Thus, we'll need two derivative linearization Einstein equations. So let's assume the metric in this case is given by equation 19. Look, here we will assume that the graviton lives on a warped background. This is the Pablo's work that assumed that graviton there live on a maximum symmetry background. It's a extension. Assume this, it is usually usual gauge, and analyze the interaction separately. So we'll analyze just quadratic, Gauss-Bonnet gravity, and then we'll analyze just cubic interaction. If analyzing interaction separately, we will obtain with help of mathematical software, because this counted a huge, you can see without them. So the analyzing linearization equation for the Gauss-Bonnet gravity for this warped background is given by equation 20. We can see that the graviton equation for the Gauss-Bonnet, we don't have high derivatives, but doing the same thing for the cubic gravity, we know that the even assumed just two initial hypotheses that I previously said, now in the linear regime, this interaction is to introduce a high derivative and the fluctuation. To get around this again, let's set more two parameters. In this case, we will set the beta 5. Interesting, because we have in this case 3 possibilities to fix this parameter, and then we will fix another one that's beta 4. If you assume there's more two fixation, we can obtain equation of motion to graviton that we don't introduce high derivative in equation. So you can do this if you assume more two fixation. You also show that this field don't present tachyonic mass, so it's stable, of course, in the linear regime. And this I'm not show here, but in this paper, you use the supersymmetry analogous structure of quantum mechanics to conclude a stability analysis for the Kaluza-Klein modes. This implies the absence of tachyonic Kaluza-Klein modes. In this paper, you show this in detail. Well, I will conclude. In this work, we've investigated the effect of a high curvature terms up the cubic order within the Brunner's model. In this cubic theory, inspired by Einstein cubic gravity, is the second order equation for the warped factor. Of course, with obtain this, we need to fix the two parameters of the cubic gravity. In the linear regime, we found of cubic gravity that describe the graviton as a massless transversal mode in a warped background, but if we need to fix some more two parameters in the linear regime. The absence of tachyonic Kaluza-Klein modes within a proposed frame modes, so this makes analysis instability. And then when they were applying and introduce the first of the BPS formalism to derivative think brand solution. Here, I'm not sure, but in this paper, we demonstrated that the massless four-dimension tensor zero mode can be effectively localized on the thinker brands and allowing for the recovery of the four-dimension Newtonian potential. So this.
Thank you very much.
And
for questions, we have one from an expert in cubic gravity and higher order derivatives. So be careful.
Thank you for your very nice talk. So,
thank you.
I mean, I would say that at the end of the day, if you impose first to have second order equations of motion on these Bernoulli answers you impose, and then if you impose that the equations of motion for the tensor perturbations are of second order in derivatives, I think at the end of the day, the theory you end up should be equivalent to this so-called cosmological Einsteinian cogravity, which has been studied before in the literature. So, of course, we're considering 5 dimensions, but I would say that I think you should check to which extent the theory you've considered is equivalent to this cosmological Einsteinian gravity. So, I don't know if you have explored this or if you have any comment on that. Thank you. I cannot hear you.
Sorry, because it's interrupted. You can repeat, please? Because the connection is not good here.
So my question is, have you checked whether the theory you have found at the end is equivalent to the so-called cosmological Einsteinian cogravity?
No, it's the analysis cosmology of this theory. I didn't do this yet, but I think it's probable do this, but in this case I didn't.
Okay, I think they should match at some point. Well, thank you.
Okay.
Is there any other question?
Hay una pregunta.
Question, online question. If there is someone online, please open your micro and ask. Albert, go ahead.
Well, my question will be the following. Whether you were thinking about generalization for more general function of curvature, and whether you thought about some comparison of your work with our work of 2007, where we studied for the first time the brain solution modified gravity in f of r. Arbitrary function of a scalar curvature. Did you develop such a comparison?
Sorry, a connection is not good here. It's because you can write the chat or someone I don't know, say to me what it. Because I didn't understand.
We developed a study of a general of a brain world solution in a f of r general gravity model, arbitrary function of our curvature. So did you compare your solutions with our solutions?
I don't know.
So if I may say something, Albert, you were dealing with f of r theories, and he is considering other invariants of the scale of the curvature. He has contractions of Ricci's and Riemanns. So the formalism is more general. So I don't think that the two approaches fit much. They are different things.
Yeah, but perhaps in some specific form of the theory which was discussed here, there should be some intersection, some similarity of solution, something like this. at least for specific form of cubic gravity.
Say yes, because when you get rid of the Ricci squared and Riemann squared terms, you should
Yeah,
get-
something like r to the cube of the scalar curvature. There should be some similarity, I think.
yeah. Okay, so, Leandro, do you want to add anything?
Yes, it's because the cubic is a more, you have more parameters to fix it, so it's more general in relation, of course, the quadratic term. So it's not, it's more general. You can fix another parameters and construct a different theories cubic. In this case, you have a relation, for example, the Einstein cubic or Lovelock or something like that.
Okay, any other question or comment online or here? No, in that case, let's thank Leandro again.
Yeah.
Okay, so let's move on now. Next speaker, if I'm not wrong, is Alana Carolina, right?
Yes, person.
Okay, so
Can you hear me?
your screen. Okay.
Tá. Posso tentar compartilhar minha tela?
Ainda não. Sim, deveria ter. Yes, you have the button. The green one.
Can I share my screen?
No, we cannot see.
I'm sorry.
You have the green button, compartir tela.
Okay?
Working. Okay. So Elena Carolina is our next speaker. She's going to speak about regular black holes in 2+1 with variety. So feel free to start.
So, good afternoon, everyone. My name is Alana Carolina. I am a postdoc student at Universidade Federal do Ceará, and I will present my job entitled, entitled Regular Black Hole in D equal 2+1 with FDR gravity. So, the experimental success of general relativity is completely, at the scale it has been tested, is completely undeniable, but we have some aspects that remain misunderstood, like the singularities and the accelerated expansion of the universe. So the FDR gravity proposed that the corrections of nonlinear terms of the Ricci scalar could lead naturally to the self-accelerated solution without resort to the dark energy, for example. And on the other hand, we have regular black holes that have well-defined curvature scales, but the cost of this regularity is the violation of the energy conditions most of the time. So finally, we can find interesting effects in lower dimensional gravity, like the Unruh effect that was initially proposed in 1+1 dimension. So trying to combine both approach, we dare to ask, just as in 3+1 dimensions, do you find regular solutions in 2+1 dimensions in a FDR gravity? If so, what is the most general method to ensure that we will have a regular solutions? Do nonlinear electrodynamics that ensure regular solutions in general relativity still ensure regular solutions in a FDR gravity? And finally, are the energy conditions still violated? So to answer these questions, we start with this following reaction with a general FDR gravity and a general nonlinear electrodynamics model. And vary with respect to the metric, we obtain the equations of motion where the energy moment tensor is given by a nonlinear electrodynamics. So the electromagnetic field equations are determined by varying with respect to the potential ME, and we will assume, and we obtain this equation, and we will assume a circularly symmetric space-time. And we will consider a radioelectric field and a scalar magnetic field. So the F-mini takes this form. So using these answers to the metric and the energy moment tensor, we find this four equation. And interesting, we have in this equation that the radioelectric field or the scalar magnetic field should be zero. So in this work, we will choose the case when we have just the electric field. So with this choice, the equation of motion from the matter sector takes this form. And subtracting two equations of motions, we have this equation that naturally leads us to this form of the FDR gravity, where we have set an integration constant to -2 lambda in order to match with general relativity in the particular case when with alpha equal to 0. So we naturally obtain the form of the FDR gravity from the equations of motion. So considering now the metric answers, the invariant scalars reaching Kretschmann are given by these expressions. And to find the regular solutions, we will adopt the He and Ma approach that began by imposing a regular geometry, which means this is scalar well-defined in our domain. And so we have that this limit should be satisfied. But since in a vacuum solution, we need to recover the BTZ case, we take this form to the metric, where the KDR is a function responsible for guaranteeing the regularity of the solution and should be expanded in this following way. This is a really important equation. So derive one equation of motion with respect to R, and after some manipulation, we obtain this relation. This is a general relation between this function KDR and the nonlinear electrodynamics source. And this is a general equation to any FDR gravity. So since the nonlinear electrodynamics should reduce to the Maxwell theory, in the asymptotic limit, this equation should reduce to this form. And when alpha goes to 0, we cover on the general relativity scale, where KDR is given by this expression. So first of all, let's analyze the BTZ-like charged solution, which means when LDF is equal minus F. So it leads through the previous equation to this KDR function. And in the asymptotic limit, when R goes to 0, we obtain this form, the dominant term of the Ricci scalar, which diverges to R equal to 0, and diverges independently of alpha and consequently FDR gravity. So the main result is the corrections of the FDR gravity are not capable of cure the singularity of this solution. And now we are interested in investigate if two nonlinear electrodynamics that conferred or that ensured regular solutions in general relativity, if this model continue to ensure regular solutions in AFDR gravity. So the first case, the nonlinear electrodynamics model is given by this equation, which leads to this KDR function. And the Ricci scalar, it is a long equation, which in the asymptotic limit R go to 0, we obtain this dominant term that diverges to R tend to 0. So we have that this nonlinear electrodynamic models don't ensure a regular solution in AFDR gravity. And the second case, we have the second nonlinear electrodynamics, which leads to this KDR solution. And in the asymptotic limit, again, we have a long equation to the Ricci scalar, but the dominant term is given by this expression, and again, diverge when R goes to 0. But when alpha goes to 0, we recover the regularity of general relativity result. And the same case in the previous analysis, when alpha goes to 0, we recover the regularity of the general relativity result. So therefore, the modifications induced by AFDR theory remove the regularity of solutions conferred by this nonlinear electrodynamics in 2+1 dimensions. So to describe the energy conditions with the appropriate physical interpretation, we rewrite the equations of motion in this way, in a similar way of general relativity, where this is the energy moment tensor of the case, effective energy moment tensor. So investigating now the energy conditions, in the first line we have the Bethe-like case. In the second line we have the first nonlinear electrodynamics case, and in the third line we have the second nonlinear electrodynamics case. And the left panels we have alpha equal to 0, which is the general relativity case, and in the right panels we have the alpha equal to 1, so corrections, including corrections of the FDR gravity. So in the first line, when alpha equal to 0, we have the energy conditions as satisfied, which is irreducible because we have the Maxwell case when alpha equal to 0. But when we include the corrections of the FDR gravity, we have that the energy conditions are violated. And in the second line, we have that when alpha equal to 0, general relativity result, the energy conditions are violated because we have a regular solution. This is a common behavior in a general relativity. But when we include the corrections of the FDR gravity, we see that the energy conditions continue to be violated. And this is a similar behavior of the second nonlinear electrodynamics case, when in general relativity case, we have that the energy conditions are violated. And when we include the corrections of the FDR gravity, the energy conditions continue to be violated. So now let's consider a hypothetical scenario in which we have a regular geometry within the constant of FDR gravity. However, it turns out to be singular in the case of general relativity. It is a hypothetical example. So we will choose this geometry, and when we calculate the Ricci and Krichmann scalar is given by this expression. And these expressions are regular if alpha is different from 0 and singular if alpha equal to 0. So we can perform now an inversion to obtain R in function the Ricci scalar and integrate the equation to obtain the FDR gravity associated with this metric, where beta dr is given by this expression. And derivating with respect to Ricci scalar, we obtain this expression. And when alpha equal to 0, we recover the general relativity case. So we can find through the equation that I showed in the beginning of the presentation, we can find the nonlinear electrodynamics associated, where D1 is a constant. And unfortunately, the equation 34 doesn't actually present a nonlinear electrodynamics, since the electric field has this form, and in the asymptotic limit when R go to infinity, the electric field is logarithmic, which is different from the classical electromagnetism. So this regularity of the solution is not conferred by, in fact, nonlinear electrodynamics. But when we investigate the energy conditions, we have that alpha equal to 0. We cover the Maxwell case, so the energy conditions are satisfied. But when alpha is different from 0, we have that the energy conditions are violated. So the FDR gravity, when conferred regularity for a solution which is singular in the general relativity case, still, even in this scenario, the energy conditions are violated. So concluding, we identified the necessary conditions to find our regular solutions in 2+1 dimensions, supported by nonlinear electrodynamics in any FDR gravity theory. We obtained a charged BTZ-like solution in the FDR gravity and investigated two models of nonlinear electrodynamics that provide regular solutions in general relativity. We found that all solutions are non-regular. And in fact, this is not surprising because the KDR functions found doesn't satisfy one of the conditions that we found previous. So therefore, the corrections in FDR gravity do not cure the singularity of the charted BTZ solution, and that remove the regularity that nonlinear electrodynamics had confirmed in general relativity. And when analyzed the energy conditions, we observed that the energy conditions continue to be violated. So attempting to answer the questions, given a hypothetical geometry regularized by FDR gravity, would the energy conditions still be violated? And so we consider it a regular geometry for alpha different from zero and non-regular for alpha equal to zero. So we define the FDR gravity as well the associated nonlinear electrodynamics. But since the electric field did not recover classical electromagnetism at infinity, regularity would not be effectively conferred by nonlinear electrodynamics. And we found that even in this scenario, the energy conditions would still be violated. So, some references, we have the work where we have a regular black holes in 3+1 dimensions with FDR gravity. The work that teaches how to construct regular black holes in 2+1 dimensions. And finally, our paper that was recently published in the archive. This is the number. So I want to thank you, my group, LASCO, and my university, Universidade Federal do Ceará, and CAPES for the financial support and the organization of this event and this incredible opportunity. So thank you for the attention.
Thank you, Ana Carolina, for your talk. Any questions or comments? Yes. Okay, first I will attend the questions in the room, then online.
Okay. Alana, do you hear me?
Yes.
Thank you very much for your talk. So here's my question. In order to obtain a regular solution, you basically see that matter content which generates such a geometry cannot come from nonlinear electrodynamics because it has not the usual Maxwell-like behavior and the asymptotic limit, right?
Yes.
Okay. So it's just a funny question. What could be the matter that generates such a geometry then? If it does not come from nonlinear electrodynamics, then what could be?
My presentation was divided into parts, into sections. In the first part, I analyzed two nonlinear electrodynamics that are in fact two nonlinear electrodynamics, and I see that these nonlinear electrodynamics are given don't produce regular solutions. In the second part, I propose a geometry to investigate if in this case we have a regular solution and the energy conditions are satisfied. And my hope is that was given by a nonlinear electrodynamic, but I see and I show that in fact it is not a nonlinear electrodynamics. I have investigated if this could be like a quantum correction, like the Casimir effect, or some density, like some densities that we have in the literature that have some good profile, like given by a potential that will give a regular solution. But I'm investigating this type of source. But the main purpose of the second section is investigate if in a regular geometry we have the energy conditions violated or not. And you see that the energy conditions are violated. But the question, what kind of matter could be this regularity? I'm still asking. I'm still searching. Thank you for the question. I don't know if I answer you.
It was a perfect answer. Thank you.
Thank you.
Okay, so we are running out of time. So let's thank Ana Carolina again.
For the opportunity.
And we have a third speaker for this session. I don't know my schedule. So is the next speaker here? Tiziano is Tiziano. So,
Hello,
hello, Tiziano.
can you hear me? Yes.
Yeah, perfectly.
Okay.
Yes, you can share the screen whenever you want.
Yes, thank you. Okay.
Okay. So, someone new in my group. Okay. So, Tiziano, whenever you want, you can start. Okay.
Good afternoon, everyone. First of all, thank you, Flavio, and all the organizers of this workshop. Next time, I will try to participate in presence. I'm glad to present my work carried out in part during the PhD course at the University of Pisa, and also during my research fellowship, Angelo Della Riccia, at the Institute of Astrophysics and Space Sciences in Lisbon. The title of my presentation is An Effective Hubble Constant in F over Modified Gravity, which draws attention to the gravitational theory of the present cosmological model to address the so-called Hubble constant tensions, a serious anomaly emerged from independent measurements of the present expansion rate of the universe, the Hubble constant, h0. This work aims to address the following question. How can we build reasonable theoretical models, and how can cosmological data enable us to discriminate among them? This question concerns modified gravity theories as alternative extensions of general relativity to provide the present cosmic acceleration. In this talk, I will explore the Hubble tension to discuss the robustness of the gravitational theory of the present concordance model. I will start with a very brief introduction of the standard lambda CDM cosmological model and the Hubble constant tension. Then I will discuss the possibility that the Hubble constant h0 may not be actually a constant, but it could evolve with redshift. Then I will discuss the theoretical interpretation of the result within the framework of modified gravity theories to ensure an effective Hubble constant with a redshift. This presentation is based on a part of my PhD work, and these 3 papers were published on APJ, Galaxies, and MNRS Letters in collaboration with a team of cosmologists. Here you can see the authors. In particular, in the latter one was written with Flavio Bombacini and Giovanni Montani. Okay, let me start. You know that the present cosmological model is based on 2 fundamental pillars, GR as the gravitational theory underlying the cosmological dynamics, and the cosmological principle. The principle of general covariance is intrinsic to the tensor formalism, and the Einstein field equations establish a deep relationship between the space-time geometry and the matter sources. The second pillar, you know, is the cosmological principle. The universe appears homogeneous and isotropic on spatial scales larger than roughly 100 megaparsec, which is well tested by the CMB observations and cosmic structures. The well-known lambda CDM includes a cold dark matter component and a cosmological constant as a specific form of dark energy responsible for the cosmic acceleration today. This cosmological paradigm describes successfully a large number of phenomena concerning the structure and evolution of our universe. However, in the era of the precision cosmology, we have obtained gradually an increasing number of measurements and better constraints on cosmological parameters. However, one of the most challenging problems of lambda CDM is the Hubble constant tension. you know that the Hubble constant H0, the present cosmic expansion rate, is nothing more than the Hubble function H evaluated today at redshift Z equals 0. So H0 is a constant by definition. However, as you can see in this plot by Di Valentino et al. 2021, measurements of H0 refer to the early universe, here on the top given by CMB measurements, are incompatible with those based on local probes in the late universe, like Cepheids and supernovae. See the light blue band. This inconsistency ranges from 4 to 6 sigma according to local probes considered. Standard candles, type wave supernovae are very useful to evaluate cosmic distance, since they are characterized by a fixed absolute luminosity. These objects were crucial to establish the accelerated expansion of the universe. In this regard, to evaluate the cosmic distance, one important quantity is the luminosity distance dl, which is written in terms of the Hubble function h of z and cosmological parameters, and depends on a specific cosmological model. Generally, astronomers prefer to use the distance modulus mu, which is related to dl through a logarithmic function. The theoretical distance modulus can be compared with the data obtained by supernovae 1A observations to constrain cosmological parameters. The H0 tension is a serious problem. It could be due to systematics in supernovae data, or it could be a signal for new physics, forcing us to reassess the fundamental peril of lambda CDM. Okay, now let me move on to the main part. We focused our analysis on the Pantheon sample of supernovae, a compilation of 1,048 supernovae in this redshift range from 0.01 to 2.26. For a statistical analysis, we use data from the Skolnick's repository, and we consider the difference between the theoretical distance modulus, which strictly depends on the specific cosmological model considered, and the observed distance modulus from supernovae, which takes into account astrophysical parameters of each supernovae. We include both statistical and systematic errors of the supernovae 1A Pantheon sample. Now, bearing in mind the Hubble tension, we wondered if the tension persists also within the Pantheon sample redshift range. This was the starting point of our redshift bined analysis. The basic idea is very simple. We divided the Pantheon into equally populated subsamples in 3, 4, 20, and 40 redshift bins to check whether the values of H0 are constant inside each bin, and so at different cosmic distances. And we perform a statistical analysis MCMC. In this regard, we needed to write a customized code to build covariant submatrices for supernovae in each bin. Finally, we extract the values of H0 for each bin, and we tested a nonlinear fitting function H0 of Z, written here on the right, where H0 tilde and alpha are fitting parameters. In particular, alpha is an evolutionary parameter. If alpha is equal to 0, obviously, then H0 is a constant, and we don't have evolution. I show you our plots. H0 seems to exhibit an expected evolution with redshift. You can see for a flat lambda CDM model a decreasing trend of H0 for 3, 4, 20, and 40 redshift bins after this redshift binned analysis. And we obtain actually similar plots also for the W0 WA CDM model, where the equation of state parameter for dark energy depends on the redshift according to the Chevalier-Polaski-Linder parameterization. We obtain consistently a decreasing trend for H0 of Z independently of the number of bins. But is it a fast and clear evolution of H0? Actually, the alpha parameter for different bins is approximately 10 to minus 2 and is consistent with 0, namely no evolution, in roughly 2 sigmas, so it is a wake evolution. These are the fit results, and the alphas are compatible with each other. You can see, for instance, for alpha equal 0.009 plus minus 0.04 in the case of 3 bins for the lambda CDM model. Now, if the observed trend is not related to a specific probe, but is intrinsically due to a redshift evolution, one may ask what happens in the early universe at very high redshifts. In other words, there is any way to adjust this bridge, solving the H0 tension to link these incompatible measurements of H0 at low and high redshifts? So we extrapolated the fitting function H0 of Z at the redshift of the last scattering surface, z equal 1100, to compare our value with the one inferred from the Planck measurements for the CMB. And we obtain an interesting result. Our extrapolated values are compatible in 1 sigma with the Planck one for the lambda CDM model. We also extrapolated H0 of z to the redshift z, roughly 11, the redshift of the most distant galaxy so far, where in principle we will be able to evaluate H0 by observations in the future. So H0 may evolve with redshift according to the cosmic distance of the sample considered. But what are some of the possible reasons for this trend? H0 must be obviously a constant by definition, so its observed evolution could be a symptom of a wrong picture of the universe. H0 of z could be due to astrophysical nature reasons, for instance, a hidden evolution of a supernovae parameter, not considered so far. Alternatively, if it is not due to statistical fluctuations or systematics, it may be a signal of a new physics different from GR. I will focus in the following on the modified gravity scenario, and I will briefly recall F of R theories. The Hubble constant tension, the need for ad hoc dark components whose exact nature is still unknown, may be considered a signal of the breakdown of GR at cosmological scales. It is believed that GR is not the ultimate theory of gravity, and this has motivated people to look for an extension to GR. Among many proposals, special attention has been paid in recent years to F of R modified gravity theories. Within this framework, the gravitational Lagrangian density is replaced by a function of the Ricci scalar, F of R, an extra scalar degree of freedom with respect to GR, which could be useful to solve open problems. For instance, a geometrical modification of GR may mimic a dark energy component. Indeed, a geometrical modification may be interpreted as an effective matter source, so the no Einsteinian terms could provide the present cosmic accelerated phase. It is often convenient to reformulate F of R gravity in the scalar tensor representation in the Jordan frame using a dynamically equivalent gravitational action. The extra degree of freedom given by the F of R function is converted into a non-minimally coupled scalar field phi. The advantage is that now we have second-order differential equations, while in F of R gravity we had fourth-order differential equations, even though now the non-minimally coupling implies no trivial dynamics. These extended theories of gravity provide different cosmological dynamics with respect to GR. Now, we look back to the trend of H0 of Z. We need to build a new theoretical model not only to mimic a dark energy component in the late universe, but also to provide a mechanism for an effective Hubble constant that evolves with the redshift. This can be considered like a criterion for viable cosmological models to address the Hubble tension. The main goal is to match independent In this regard, in our third paper, we have demonstrated that the scalar field dynamics in the Jordan frame may be lead to a redefinition of H0. Note that in the Jordan frame, we have an effective Einstein constant key related to the scalar field. We rewrite the potential as a cosmological constant term plus a small deviation. Neglecting this latter term, we end up in a Hubble parameter that is quite similar to the lambda CDM, but now with an effective Hubble constant that evolves with the redshifts, with Z. The non-minimally coupled scalar field plays a crucial role. Furthermore, solving the cosmological dynamics in the Jordan frame, we reconstruct analytically the expression of the scalar field potential. In particular, we require an ansatz for phi of Z, and also we impose the results of H0 of Z from our previous redshift bined analysis of the Pantheon sample supernovae to infer the form of the scalar field potential in the Jordan frame. These are our results. We can see in the potential profile the occurrence of a flat region at low redshifts, a scalar field in a near frozen dynamics mimicking a cosmological constant term. Furthermore, at the same time, this potential also provides a decreasing trend of H0. we compare our analytical approximated solution with a numerical solution obtained without any ansatz, and they are in good agreement for low redshifts in the dark energy dominated universe, where our starting hypothesis for the potential is valid. Finally, expanding our analytical solution for low redshifts, we can calculate the form of the f/r function associated with the potential profile in the Jordan frame. And we found that the form of the f/r function in the well-known quadratic gravity with a quadratic correction in R. I would like to stress also that this is an approximated solution for low redshifts, and it can be shown that the lambda CDM is recovered for alpha goes to 0. So alpha, this parameter, in addition to being the physical parameter that describes the evolution of H0 of Z, also denotes small deviations from GR. Here, B0, B1, and B2 are parameters related to alpha and the value of the scalar field today. In conclusion, we have provided a new interpretation of the tension with an effective Hubble constant. It could be no longer a discrepancy between independent measurements of H0, but it may be an intrinsic evolutionary behavior in an extended modified gravity scenario. But of course, we need to obtain better constraints on the evolutionary parameter alpha with the new incoming surveys concerning the large-scale structures like Euclid and DESI, or also other cosmological probes like the Pantheon Plus sample or quasar and gamma ray burst that can provide, in principle, a larger redshift range to investigate this problem. Also, I showed that this problem can potentially provide a mechanism for new cosmological models and new physics with respect to GR. And thank you for your attention, and I'll be happy to answer your questions.
Time for questions, complaints, criticisms. Nothing. I think people are tired here. Anything online? Any comment online? Feel free to open your micros if you want to ask anything. And there is one question here.
Tiziana, it's Tiago here. Just on a personal, your personal opinion, what do you expect from these new surveys? What do you think might come up from them? Any expectations?
Thank you very much for your question. Yes, with these new surveys, you mean the new surveys in the large scale structure, right?
Yes.
Yes. With concerning my work, these new surveys can be very useful to obtain constraint also on the question of state parameter for the dark energy W of Z. I showed my results mainly for the lambda CDM model, but actually we obtain similar results also for the WCDM model by using the Chevalier-Polaski interparameterization, but the decreasing trend of H0 of Z still remained. But with these new surveys, we can have better constraint on this W parameter, and also the distribution of matter in the late universe can give us new information about our universe. So they can provide new data to obtain better constraints also on modified gravity theories.
So if you had to guess, would you say they would bring us closer to the standard model or further away, increasing tensions?
Yes, this is a challenging question. At the moment, we have some preliminary analysis or forecast about this new surveys, but at the moment it's hard. It's difficult to provide an answer to this question. But yes, it would be very interesting to investigate this problem in the future.
Thank you. Thank you.
Thank you very much.
Okay, so it's time to finish. Let's thank Tiziano again.
Thank you. Thank you.
So now we'll have a break of 20 minutes or so. Okay, we'll be back. Yeah. No, non vedo qua.
No, se no cos'è la scheda? D'accordo, io volevo...
No, Sebastiano.
Ci siamo coordinati.
So, welcome back. We now start our last session of the workshop, and our first speaker is Sebastiano Segreto from Roma, and he will present us his work on n-dimensional non-commutative GUP quantization and application to Bianchi-1 cosmology.
Really? No. Done. Okay, thanks for the presentation. Thanks to the organizer for this opportunity to talk. Thanks also to the survivors of the last section. And today we're talking about non-commutative generalized uncertainty principle theories, or good theories in short, as a quantization framework in cosmology. This is the outline of the talk. In the first part, I will briefly introduce group theories, what they are and why we are interested in this kind of theory. Then I will present a specific model that we have studied in a recent work with my supervisor, which is in preparation. And in the end, we will see a simple application in cosmology of this quantization framework. So, generalized uncertainty principle theories are quantum non-relativistic theories, which are based on a deformation of the usual Heisenberg uncertainty principle, and they can be considered related in the low energy limit to string theory. The rigorous way to deal with this kind of theory is to deform the usual Heisenberg algebra between the quantum conjugate operators, or in other words, we need to deform the canonical structure of quantum mechanics. And when we are dealing with this kind of theory, we face two main consequences, possible because it is model dependent. First of all, the appearance of a non-zero minimal uncertainty in the configuration variables, the position if you want, which can be interpreted as the emergence of some minimal structures in the configuration space. And in more than one dimension, it is possible to obtain non-commutativity in the coordinate operators, which somehow is a form of non-commutative geometry. Why we are interested in these theories? Well, our goal is to implement, as I say at the beginning, this kind of framework in cosmology. And we can do that because usually in cosmology we consider homogeneous space-times. This means that our gravitational field has a finite number of degrees of freedom, and hence in this kind of context, one-particle quantization schemes are well-grounded. So the idea behind these kind of works is to modify the algebra in order to introduce new features in the dynamics of the system. So in this case, the early universe, for example. And these features in principle should come from some underlying fundamental theory. There is several classes of group models. Here I only talk about this kind of model in which the modification of the commutator is given by this f function, which depends only on momentum. We can impose some condition, even if it's not strictly necessary, but it's a good condition to have a well-behaved commutator. And it is clear from the algebra that the natural representation is a momentum space. Here you can see the representation of the operators in the momentum representation. So P, it is just the multiplicative operator, Yx, it is a differential operator with this extra factor f in front of the derivative. At this point, what we have to do, we need to construct our theory step by step from the beginning. So we need to define our operators in a proper way. We need to check their domains. And all of this has to be done in a Hilbert space well-defined. So in this case, usually the Hilbert space will be the space of all square integrable function over some configuration space with a modified Lebesgue measure, which is needed to assure some properties of our fundamental operators. one of the most important thing to do is to check if we are dealing with self-adjoint, actually essentially self-adjoint operator, especially for the position operator. Indeed, in this kind of theory, this is not the case most of the times. At this point, we can define a physical domain for our theory, such as the one that I wrote here, even if other conditions can be imposed. It depends on what we have to do. Now we are ready to search for a minimum if it exists in the position expectation value. We can use several methods. And in particular, it is important to understand the physical states which realize this condition. These states are very important. They are called maximally localized states. And they are important because if we are dealing with a minimal uncertainty position which is different from zero, the position representation at formal level still exists, but now there is a limit in localizing objects. So this means that the physical meaning of position representation is lost because it is a pointwise concept. And one of the possible way out to recover information in position was proposed first in this paper, that one, by Kempf and collaborators, and it consists in using maximally localized states as a basis to construct a new representation, which is called quasi-position representation. So in this case, what we have to do, we need to project our physical states onto the maximally localized states, and we will obtain new wave functions, which are called quasi-position wave functions, and they will depend on a parameter C, which is the position expectation value of the maximally localized states. And the physical meaning is the following. We are dealing at this point with objects which are describing probability amplitude of find a particle which is maximally localized around a certain point. So the model that we have studied is the one that you can see here. It is described by this algebra. This is the deformation of the commutator relation between the conjugate operators. Beta is just a positive parameter which controls the deformation. We can impose that the momentum operator still commute as in the ordinary theory, but you cannot see maybe here, but if we impose the validity of the Jacobi identities, we can find that the commutator between coordinate operators is different from zero. This is essentially the non-commutativity of the model. This commutator will depend from this operator, which is the generalization in this kind of theory of angular momentum, the angular momentum, or if you prefer, the generator of rotations. What can we say just by looking at this algebra? Well, first of all, it is an extension of the original model proposed again by Kempf and collaborators for the first time. And we see that in this kind of algebra, the rotation invariance is preserved. This is suggested by the presence of the angular momentum, but the translation invariance is lost. So our concern was to find a way to recover information on position. We were able to find maximally localized states along just one direction. So there is a limit to localizing objects in every direction. But since there is no commutativity in this kind of model, we are not able to find states which are maximally localized at the same time in every direction. And this is a problem because in this way we cannot map the whole configuration space and recover information on position. So we propose the following solution. We notice that actually there is just one state in this theory, which is maximally localized in every direction at the same time. And it is the state that you can see here in n is the number of dimensions in which we are working. And this state is centered the origin of our momentum space, and it is a rotational invariant state. So what we've done is to consider this state and translate it in a proper way, because translation are tricky in this kind of theories, to generate a new family of states to be used as a quasi-position basis. The states that we have obtained are the following one. You can see this extra factor here with respect to the previous formula.
And now, if we decided to use these states to map the configuration space, and so in order to understand what kind of picture of the configuration space we are obtaining, we computed the uncertainty in a generic direction. And this is the result. This is very interesting and problematic at the same time, because if we use these states as a basis, we notice that the uncertainty position will depend on the position expectation value of these states in or the other direction. And this means that our space, our configuration space with respect to the localization properties is inhomogeneous. In other words, it depends, the localization property will depend on where we want to localize. So away from the origin, the localization is worse. And we can only strictly talk about localization only around the origin in this kind of theory. So now our framework is ready, and we decided to apply this to quantize a Bianchi-1 model. This is the usual space-time metric. We decided to use it the Mizner variable. So we introduce alpha, which is related to the isotropic volume of the universe, and the gamma variables behind here, which are the space anisotropies. And as usual in this kind of theory, we can compute the Hamiltonian constraint, which is the one you can see here. We needed to add a positive cosmological constant for consistency, and we proceed to quantize this model. Now, the quantization procedure in cosmology are subtle. There are several ways to do that. We decided to use the Vilenkin approach, and this approach essentially you can separate your system in a semi-classical part, which in this case is represented by the alpha variable, essentially the volume, and in a small quantum subsystem. On a general ground, Vilenkin was able to show that for the semi-classical part, it is possible to recover an Hamiltonian equation for the dynamic. And thanks to the semi-classical part, it is possible to obtain a real Schrödinger equation for the small quantum subsystem. This is the ansatz for the wave function in momentum space of the whole universe. You can see here the semi-classical part, which has a WKB form. And this is the quantum part, the one in which we are interested. We were able to do all the calculation in momentum space, and we obtained the following real Schrödinger equation for our quantum subsystem. This is the Lapse function, which represents the gauge freedom of our theory time. So we can set this object in a proper way in order to obtain just the Hamiltonian of a free wave particle. And now we can solve the dynamics. So this is the wave function of the universe in momentum space. It is a free particle, so it is just these two deltas here with this factor in front of everything for convenience. And since we have now we have this new representation, the quasi-position representation, or if you prefer in this case a quasi-anisotropist representation, we can write down the wave function for the quantum part of the universe in this representation, which is the one that you can see here. Nevertheless, the general solution is given by a superposition of this object. So to describe our universe in a more general way, we constructed a wave packet. This is the standard construction. You can see here the eigenstates of the Hamiltonian. This is a profile. We choose a Gaussian profile for convenience. And this is the time evolution factor of our system. What are the dynamical features that we have found? Well, first of all, the wave packets start spreading in different directions, but there is something strange going on. Indeed, the peak of the wave packet, even if it's lowering in time, and this is good because if you want, it means that the evolution is unitary, it's not moving from its original position. And it is very different from what happens in organic quantum mechanics. Indeed, as you know, in that case, the wave packet escapes towards the region with higher anisotropies because the peak is moving while spreading. But this is not the case. What are the consequences? Essentially, the initial configuration of our wave packet in this kind of theory will be the most probable one at least until the wave packet is not completely spread in the configuration space. Or in a more quantitative way, the initial configuration will be favored from a probabilistic point of view for a longer time with respect to the ordinary theory. Here you can see a pictorial representation of what I've said. This is the wave packet, in this case, centered around the origin, some initial time, and this is its evolution in time. As you can see, the peak is lowering. You can see it from here, from the vertical axis, but it's not moving. This is actually general properties of the model. I mean, it does not depend on where you pick the wave packet. So it is true also for different configuration in a region which is allowed by the Delaunay approximation. And also we need to consider the fact that maybe in our theory is not doesn't make any sense to consider wave packet picked too far away from the origin because of the localization properties. Well, so in conclusion, we have seen that group theories are able to provide in our model minimal structures and non-commutative the coordinate operators in our configuration space. We have seen how they provide a good framework in mini superspace that is to quantize cosmological models. And then I show you a precise n-dimensional non-commutative model, which poses significant challenges in localization, but we were able to recover information in position, generalizing the quasi-position representation. And in the end, I'll show you these particular features of the dynamics of a Bianchi one universe in this quantization framework. And this suggests that maybe studying more complex models, we will obtain something interesting on the dynamics of our universe. That's it. Thank you for your attention.
Thank you, Sebastiano, for the nice talk. So, questions?
Thanks very much, Sebastiano, for your nice talk. You have mentioned at the beginning of the talk about the minimal structure from GOOP.
Yes.
Can you give us some example or what kind of structure we have? Thanks.
Well, essentially, I just try to generalize the language, if you want, because usually in this theory, the minimal structure are minimal length. I mean, if you're working with the usual position and momentum operators, so the ordinary, so the quantum mechanics of in the real space, this minimal structure will be a minimal length, for example. In the configuration space of cosmology, of course, this minimum is related to other variables, such as, for example, the anisotropies. So I just generalize this the vocabulary of minimal length to minimal structure, because in the mini superspace, for example, it is not a minimal length. It is a minimal uncertainty on the anisotropies.
Thanks very much.
Thank you for your nice talk. First of all, my question is, in which kind of experimental apparatus would be possible to probe these kind of theories?
Okay, well, we need maybe to make a distinction. If you are considering this kind of modification of the commutator, if you are thinking of real space, maybe this of course will depend also on for example, the parameter beta. Maybe there are some experiments which, at my knowledge, regards optical physics and the decoherence properties under this kind of commutation relation. I don't know, of course, the precise setup of how you can do that. But it's important to say that maybe from a physical point of view, see this kind of commutation relation in a configuration space of cosmology could be something different. I mean, we expect in cosmology that the scales of this correction is the Planck scale, of course. Clearly, if there is some kind of correction to, I don't know, atomic physics, if you can consider by this structure in an effective way, it could be that this kind of correction could enter different scales. I don't know. So I will make a distinction between these two physical contexts.
Thank you.
Hi, thank you for your talk. I have a question about observables. Is there any way to define observables, such as maybe the volume that you mentioned? So you talk about the state, but is there any way to define observable for the Hilbert space? Or
Yeah. Can you rephrase the question, because I'm not sure I understand it.
I mean, you constructed some like a Hilbert space, and you define a state and a Gaussian state.
Yeah.
So for this Hilbert space, is there any observables like operators?
Yes. Well.
Yeah, like physical observables, like the volume or something.
I guess you can do that. I mean, I guess you can do that. We didn't explore, let's say, this part of the formulation of the Hilbert space. We didn't care so much at this point. I mean, of observables. But I guess you can do that without any particular problem.
Okay, thank you.
So let's thank again Sebastiano. And our next speaker is Gabriele Barca. He is on a way of completing his PhD. And he will present us his work on non-singular gravitational collapse and perturbation with a deformed algebra.
Can you hear me? Oh yes, thanks for the introduction and thanks for inviting me to this talk. Yes, today I'm going to talk about the implementation of a modified Heisenberg algebra to gravitational collapse. And okay. So I will first of all introduce the modified Heisenberg algebra and also give some motivations of why we want to study this kind of formulations. And then I will implement it on the gravitational collapse, both in the Newtonian framework, which is given by the Hunter model, and also in the fully general relativistic framework, given of course by the Oppenheimer-Snyder models. And then I will study the behavior under small perturbations. So these kind of algebras, as we have already seen with Sebastiano, are usually studied as functions of the momentum. In particular, I will study this algebra here, which is inspired by polymer quantum mechanics, which is a procedure of quantization of a lattice similar to loop quantum gravity, and also inspired by the group coming first string that Sebastiano presented, except this will have a minus sign instead of the plus sign of the group. However, I will not study the quantum framework, but just the semi-classical framework. And basically the limit, the semi-classical limit of the deformed computational relations is deformed Poisson brackets instead. And this kind of algebras in general introduce additional structures like, for example, minimal length as the standard group, or maximum energy, cutoff some momentum, etc. And they are used specifically in cosmology for this reason. And as an example, we can see here the modified Friedmann equation coming from a similar algebra to this. And this Friedmann equation is able to remove the cosmological singularity, for example. And these kind of algebras are also useful to extract some phenomenology coming from more fundamental quantum gravity theories. So the Hunter model is a Newtonian model of a spherical symmetric cloud collapsing under its own gravity without pressure. So here we see the Newtonian. A given spherical symmetry, our only dynamical variable will be the radius, and P is the conjugate momentum. And we defined the variable A, that is basically just a rescaled radius. And then we have the standard definition of the Schwarzschild radius. So on a classical level, with the standard Hamilton's equation, we obtain this differential equation for the variable A. And it's quite clear that this is singular. And indeed, as we can see here from the dashed black line, the collapse will happen and will end at a singularity. But if we use the modified algebra to derive the equations of motion, we obtain this modified differential equation for the variable A, and there is this correction factor here depending on the deformation parameter mu of the algebra. This correction factor introduces an asymptotic behavior, as we can see here on the continuous red line. And of course, the asymptotic value will depend as this form and will depend on the deformation parameter mu. In this case, of course, since this is the Newtonian framework, we have to ask that the Newtonian approximation still be valid by requiring that the asymptotic value of the radius be much greater than the Schwarzschild radius. With this requirement, we can obtain a lower limit for the deformation parameter mu. As we can see here, this will almost always be of order unity. Bigger than unity, but not by much. And it's peculiar how a correction that is of order unity in Planckian units is able to introduce a macroscopic correction to this framework. So if we move on to the relativistic framework, in the Newtonian formulation for the Oppenheimer-Snyder model, we have three contributions. One coming from the outside metric, one coming from the boundary metric, and the one that interests us is the one coming from the internal metric of the cloud. And this results to be very similar to Netfeller W Hamiltonian with positive curvature. So here A is equivalent to the cosmological scale factor, but here will be related to the radius of the cloud, of course. Then we have PA, which is the conjugated momentum. There is a volume scale here appearing, this B. K is the curvature, and this M is related, of course, to the mass of the cloud and is a constant term. So again, with the standard Hamilton's equation and modified framework, we obtain this differential equation for A. And comparing it with the Newtonian one, we can find an identification for the curvature of the inside of the cloud. And again, of course, the solution will be very similar. We have the black dashed line that falls into a singularity. With the modified algebra, we obtain this deformed differential equation for A, and this correction factor is different from the previous one. Of course, it still depends on the deformation parameter of the algebra, and it is still able to introduce an asymptotic behavior and to halt the collapse before the singularity. However, the expression for the asymptotic radius is quite different. And first of all, there is a square root, so we have to impose a reality condition. And this will impose another lower limit on mu, as we will see shortly. But also it is important to notice how this, by construction, as long as it is real, will be always greater than half of the initial radius of the cloud. And of course, we could also here impose, if you want to have a visible final configuration, we could impose that the final radius is greater than the Schwarzschild radius. However, this is not really needed because, again, it's very rare to have a Schwarzschild radius that is bigger than half of the original radius. In any case, we obtain these two lower limits for the deformation parameter, one coming from the ideal condition, the other coming from the Schwarzschild radius. They are of very similar order in a way, and we have the volume constant is appearing here. And this makes it so that these values are very, very small in Planck units. So again, we have that a Planckian correction is able to introduce macroscopic change in the dynamics. So now let me move on to the perturbations. For the Newtonian framework, we use the Euler representation. So we perturbed the continuity, the Euler and the Poisson equation, and we define the density perturbations in this way and expanding them. So the special part is, as usual, the standard three-dimensional spherical harmonics and the Bessel radial function, and a time-dependent amplitude. This way, the density perturbation is an eigenfunction of the Laplace operator, and we can obtain a differential equation just for the amplitude. Then we substituted the asymptotic behavior of the background, and for this framework, we used polytropic equation state. So when we use the standard singular background, we see that most perturbations diverge, except when gamma, the polytropic index here, is equal to 5/3. In that case, the amplitude of the perturbations is constant, but the frequency diverges. On the other hand, when we substitute the asymptotic background, we obtain a length scale, which of course depends on the asymptotic radius and therefore on the deformation parameter. And this acts as some sort of a Jeans length, in that perturbations that have an initial wavelength smaller than this fundamental length will not diverge and will be ultimately damped, while perturbations with initial wavelength greater than this length will diverge. Regarding the relativistic framework, we had to rewrite the metric using conformal time and the standard angular radius variable x. So this is our metric. Then we, of course, we perturb the metric and the density. In this case, we have to expand the density perturbations in four-dimensional hyperspherical harmonics. And again, we can obtain an equation just for the amplitude of the density perturbations. In the relativistic case, we cannot use a polytropic equation of state because it is not a solution of the relativistic continuity equation. So we chose to just keep the speed of sound as a free constant parameter. In the singular unmodified background, we obtain this behavior for the perturbations. There is this parameter sigma here that depends on the speed of sound, and it can be imaginary. However, here at a zero is the time of the collapse, and this will always have a negative, this exponent will always have a negative real part. So all perturbations will diverge in this case. If we substitute instead the modified background, the asymptotic background, we have that density perturbations will have an exponential behavior depending on this parameter nu here, which again is a square root depending on the speed of sound and on n, which is the order of the hyperspherical harmonics and basically acts as an inverse wavelength. So we have that these perturbations, we can find a minimum value of the speed of sound, above which this quantity will be imaginary and the perturbations will be damped and raised. Vice versa, for each value of n, for each value of the speed of sound, we can find a minimum value of n under which this will be imaginary. So again, if we invert the quantity n, we have again found somewhat of a Jeans length above which the perturbations will diverge. So to conclude, I have shown how these kind of modified algebras are able to remove singularities, both cosmological and gravitational. And in particular, in this framework, they are able to introduce an asymptotic behavior. And also it is important to note that corrections of Planck order are able to have microscopic effects. And also I found a greater parameter space for which the final configurations are stable under small perturbations. This work can be continued in a few different ways. For example, by implementing more realistic equations of state that could help address the violations to the mass limit of stars that have been observed, that have been obtained in recent observations. We could also use different forms of modified algebras, and we, for example, already know that there is an algebra that is able to introduce an oscillating behavior instead of just an asymptotic one. And it could also be interesting to see what happens if the asymptotic value of the radius is below the horizon, and see what happens in that case. Thanks for your attention.
Thank you, Gabriele, for the nice talk. And now, question time. So, I want to begin with our expert of gravitational collapse.
Well, well, thank you. I'm not such an expert, but well, thank you so much for your very, very nice talk. And I find it like very, very interesting actually, because when we started studying gravitational collapse in modified gravity, these were precisely the kind of effects that we were looking for. And it's very nice to see that when you introduce, as you said, Planckian corrections, you get results that are truly, truly macroscopic. So it's very, very interesting.
Quite a surprise, yes.
It's very, very interesting. And my question is that when you have these modified dynamics, the equation for the density and well, the Friedmann equation, the modified Friedmann equation, which is very similar to that one, yes, which is very, very similar to the one which is used, for example, in loop quantum cosmology, etc. Here, actually, this could come from an effective theory, right? Like an effective classical theory.
Yes. Basically, these kind of modified algebras can be considered as phenomenological ways to introduce effects from more fundamental gravitational theories, quantum gravitational theories, in a simpler and effective way.
And my question is, do you have any clue of which kind of effective theory could produce that Friedmann equation?
What do you mean? What kind, in what sense?
Maybe, for example, that there could be an f of r theory, just saying an f of r theory which reproduces that Friedmann equation, for example, or...
Yes, actually, I have been interested in that for a while. I still haven't done that because of lack of time, and also I'm not too familiar with the modified gravity frameworks in general. I'm starting to study them. But yes, it would be very interesting to go backwards from a modified Friedmann equation and try to find some modified Lagrangians. I had a colleague send me a few papers about reconstruction methods, and I'm starting to reading those, and yes, I would like to study that at some point in the future, but okay. I still don't know.
Okay, so if you try to look at these things, write to me or something, because when you have modified gravity theories, the problem is that you do not only modify the equation for the interior, you can possibly also modify the exterior. And using the junction conditions to glue both solutions together, you can get funny results. So you can also expect modifications on the exterior spacetime, and funny things could happen. So, please, if you start working on this at some point.
In contact with Flavio and...
Exactly.
So, yes.
Exactly. So thank you so much.
A new love is born.
Maybe next year you're gonna come us and tell us the progress on the.
Exactly.
Thank you very much for your talk. I also have a question that is exactly in this slide. I was wondering, when you deform the algebra in such a way, the fact that the classical solution doesn't have a singularity, how much will that depend on the choice of the deformation of the algebra? Do you have?
Yes, I suppose that, for example, in this particular case, I'm not so sure, but for example, there is another algebra that has a square root here, like square root of 1 minus the square is squared. In that case, for example, in order to keep the computation relations imaginary, there is an automatic upper limit on the expectation value for the momentum. So especially in cosmology, where the momentum is related to the matter content, the energy density, because of the atomic constraint, that is basically the reason this kind of algebras introduce cutoff from the momentum that corresponds to a cutoff in energy density. So that's why the singularities are removed. In this case, without the square root, I think Sebastiano did something about that. And maybe there is something to do with the resummation of the series when you define operators in a certain way. I don't remember exactly, but also in that way, maybe there is some limit on the momentum. Because, for example, with the group, the GP, where you have a plus sign, in that case, you don't have an upper limit on the momentum. And we studied that, and in that case, the singularity is still present.
Okay.
So
there
are some indications for the different reasons, maybe.
Okay, so the key part is probably that there is an upper limit in the momentum, right?
Yes.
Okay, thank you.
Probably.
So first of all, thanks very much for your very nice talk. I have a question about this modified Feynman equation. I can imagine that you said that you avoid the singularity, so we have a bounds. Can you imagine? Yes.
Actually, with this one, that comes from this algebra, also in cosmology, there will be an asymptotic behavior with this one specifically.
Okay, so my question is the following one. You have in this kind of bounds a minimum of the scale factor. And if you have this kind of minimum, you have some relationship with, for example, this deformed commutator, in the sense of we can go beyond a minimum scale, or nothing about that.
So, what do you mean exactly?
I mean, if you go beyond, you are near to the bounds. In this case, you have this deformed commutator. So, and if you impose that you have a minimum scale or something like that, or if they are kind of, you have a relationship between this, the value of the scale factor at the bounds and the value of mu. That's my question.
Okay, of course, in the cases where there is a minimum scale of some sort on the, actually a minimum value in the scale factor, the minimum value always depends on the deformation parameter. And on a semi-elastic level, the minimum is introduced because otherwise the scale factor would be imaginary. On a quantum level, it's a matter of expectation values of operators that usually follow the classical trajectories because of the Ehrenfest theorem. And in that case, it's probably more a matter of momentum cutoffs, energy cutoffs. I don't know if that answered your question.
Thanks.
Okay, let's thank again our speaker, Gabriele. And let's move to the next speaker, who is gonna be Eleonora Giovannetti, which is an online contribution. Eleonora, are you there?
Yeah, can you hear me?
Yeah. Hi.
Can I start sharing? No.
Yeah, please share your presentation. Yes, that's you. Okay.
Can you see the slides?
So yeah, Eleonora will present us her work on the isotropic bounds of Milankin and the Bianchi-Nani model. And so when you want, Eleonora, you have 20 minutes.
Thank you. So first of all, good afternoon to everyone, and thanks to the organizers for giving me the opportunity to talk at this conference. This presentation is based on the paper mentioned here in collaboration with Professor Giovanni Montani from La Sapienza. That is about the quantum behavior of the anisotropies in a Bunsen scenario. This is a brief outline of the presentation. In the first part, I will start by presenting the main ingredients of our model. So first, I will recall you what is the big bounce and what are the main motivation at the basis of our investigation. What is the cosmological model that we take into account, and what are the two approaches that we use in our study. And in the second part, I will present you the main results of our analysis, and we'll finally outline some concluding remarks. So what is the big bounce? The big bounce is the best attempt to solve the initial singularity. It has been obtained in the context of loop quantum cosmology, and basically it's the result of the fact that geometrical operators like area and volume have discrete spectrum in loop quantum gravity. And in the cosmological context, the main consequence is that the two singular branches of the universe evolution that you can see here represented by the dotted lines are replaced by this continuous blue trajectory, that is the bouncing trajectory, in which the initial singularity is replaced by a bouncing point in correspondence of a minimal value for the universe volume. The two main motivations at the basis of our analysis are the following. The first one is that the big bounce has been characterized mainly at a semi-classical level, but it's obviously a quantum phenomenon in the sense that it happens in a region of the universe evolution in which quantum effects are not negligible. So it's important to pay attention to the hypothesis under which our semi-classical description is reliable, and if it really captures the nature of the quantum big bounce. And the second one is somehow related to the first one in the sense that the anisotropic degrees of freedom play an important role in characterizing the nature of the big bounce. And in particular, if we even if we consider a very simple cosmological model such as the isotropic and homogeneous one, and we start with a highly localized wave packet on our semi-classical trajectory, we have that anisotropic degrees of freedom can arise and are the main responsible for the spreading phenomenon of our wave packet. And in the end, we will deal with a complete delocalized wave packet, and so our semi-classical description is not satisfactory anymore. So the aim of our analysis is demonstrating that it is possible to start with a quite general cosmological model, such as the Bianchi-Knight one, and to maintain the universe in a quasi-isotropic state across the bouncing point by preventing the divergence of the anisotropies. So we consider the Bianchi-Knight model, that is the most generic anisotropic but still homogeneous model, that has been mainly studied in the Misner variables that are a set of three variables. In particular, alpha is called the isotropic variable and is related to the universe volume, whereas beta plus and beta minus are the two anisotropic degrees of freedom. In this set of variables, the Hamiltonian takes a very simple form. As you can see here, the kinetic part is diagonal, and we have a sort of potential term here that depends on the two anisotropies. And this potential has a very non-trivial expression, but it has some symmetries. As you can see from this equipotential line, it is basically a triangular potential well in which the walls are exponentially steep and move outwards while approaching the singularity. in this model, the singularity is approached for alpha that goes to minus infinity. And usually, but to study this model, it is used the Arnold-Dessel-Misner reduction of the Hamiltonian. In particular, alpha is chosen as time variable, and then the Hamiltonian constraint is solved with respect to the momentum associated to the variable alpha. And in this way, the Bianchi-Knight dynamics is mapped with the dynamics of a two-dimensional pinpoint particle, in which alpha is the time variable and beta plus and beta minus are the two spatial degrees of freedom. In particular, the dynamics of the point universe inside this potential wall is consists of an infinite series of bounces against the walls while approaching the singularity. And the properties of the dynamics can be analyzed by studying the reflection law. And the main result is that the dynamics is singular and chaotic. The second ingredient of our analysis is polymer quantum mechanics, that is an alternative representation of quantum mechanics not equivalent to the standard Schrödinger one, and that is able to reproduce loop quantum cosmology at an effective level. So in this sense, it is a good instrument to introduce quantum gravity effects in the dynamics by using a simple mathematical framework. In particular, this representation is useful when you want to describe as discrete your configurational coordinate. In this notation is Q, as you usually do when you want to introduce cutoff effects on your cosmological degrees of freedom, for example, the scale factor or the universe area or the universe volume. And then the consequence is that the momentum conjugated to the variable Q doesn't exist as a well-defined Hermitian operator. As you can see here, the operator Q is still well-defined, but only the exponentiated version of P is well-defined, and in particular, it corresponds to the translational operator. So the standard procedure in polymer is to introduce a lattice, as it is written here, that is characterized by a constant lattice spacing that in this notation is mu and is called polymer parameter, on which defining a regulated version for the momentum operator. In particular, by using the action of the translational operator on the lattice, one can obtain this version of the momentum operator by using the same function. If one substitute this same function in the Hamiltonian operator, one obtains the regulated version of the Hamiltonian operator through which studying the polymer modified dynamics. The third ingredient is the Vilenkin proposal that comes from the need to recover the wave function interpretation in the Wheeler-DeWitt formulation, and that is mainly based on the assumption that the phase space is divided into a semi-classical region and a quantum one. In particular, in order to recover a proper time evolution in the Wheeler-DeWitt formulation that is affected by the so-called frozen formalism, three main hypotheses are needed. The first one is that the quantum region is small and the effects on the semi-classical phase space are negligible. The second one is that the universe wave function can be written as the product of a semi-classical contribution, WKB expandable in H bar, and a pure quantum one that is, in this notation, is the function key. And the third one is that the dependence of key on the semi-classical degrees of freedom is only parametric, and this corresponds to a sort of Born-Oppenheimer approximation. So to summarize this, the main hypothesis is that the quantum region of the phase space is small and the quantum degrees of freedom are fast with respect to the semi-classical one. And this is necessary to reconstruct a time evolution, and in particular to use the semi-classical degrees of freedom to reconstruct a clock. In fact, by using this hypothesis, it is possible to demonstrate that from the Wheeler-DeWitt equation, one can obtain the Hamilton-Jacobi equation at the zero order in H bar, the continuity equation at the first order in H bar, and these two equations together characterize the semi-classical part of the wave function, and also the Schrödinger equation that characterizes the wave function key, that is the quantum part of the wave function, and in the end we deal with a proper time evolution for the quantum system and a semi-positive defined probability. in our model, we put together the Vilenkin approach and the polymer formulation. So first of all, we reformulate the Vilenkin approach in the polymer in the momentum representation in order to make it compatible with the polymer formulation. We take in consideration the Bianchi-Knight model with a Taylor expanding potential up to the second order. In particular, we use the hypothesis that far from the bounds, the anisotropies are small, and in particular, we consider, according to the Vilenkin approach, our anisotropies beta plus and beta minus as our small quantum degrees of freedom, whereas our classical phase space is made of 2 degrees of freedom that are the variable A, that is the universe area, and the free scalar field phi. From this Hamiltonian, we can derive, as I said before, the Hamilton-Jacobi equation, the continuity equation, and the Schrödinger equation that can be analytically solved. But before going to the quantum behavior of the anisotropies, that is the core of the work, we first focused on the classical dynamics of the semi-classical background. In fact, as you can see here, we decided to describe it as discrete the universe area A, and we introduced the polymer version of the momentum operator here. So the first step is to verify if the polymer effects are able in this model to regularize the initial singularity and introducing a big bounce. So first of all, let's analyze the semi-classical sector of the Hamiltonian. In particular, in order to derive the classical dynamics, we write the Hamilton equation. We choose a specific time gauge and impose some initial conditions. And in the end, we find that the universe area experiences a bouncing behavior. So the Bianchi-Knight model is not singular anymore. So polymer effects are able to reproduce a semi-classical background in this case. And this is a key ingredient for the following analysis at a quantum level regarding the anisotropies. In fact, as you can see here, this is the Schrödinger equation that governs the quantum behavior of the anisotropies. And it is basically an equation for a time-dependent harmonic oscillator. And here the term in brackets is related to the Taylor expanding potential of the Bianchi-Knight model. And the time-dependent frequency of this harmonic oscillator is exactly the universe area. So in this case, if we change the dynamics of the semi-classical background, we change the set of eigenstates of the harmonic oscillator, and we end up with a different behavior for the anisotropies at a quantum level. So we choose to deal with a semi-classical background that is regularized thanks to the presence of the polymer effects. So for the time-dependent frequency, we use the bouncing trajectory that we found before. And we analytically solve this equation, and we find the set of eigenstates of the harmonic oscillator that corresponds to the wave function for the anisotropies. Here in this plot, you have the wave function for the first 3 energy levels. So the key point is that thanks to the presence of the Bianchi-Knight potential, we have that the polymer effects that are applied only on the semi-classical background are able to enter the quantum dynamics of the anisotropies, so to affect the dynamics of the anisotropies at a quantum level by means of the time-dependent frequency of the universe area. Now, in order to analyze the quantum behavior and to verify if the anisotropies are divergent as in the standard case, or if their behavior is regularized by the presence of the Bianchi-Knight potential and the polymer effects together, we have to investigate and to compute the mean value and the variance. In particular, we use the approach of the creation and annihilation operators, so we are able to compute the mean value and the variance in an analytic way. And the result is that the eigenstates are quasi-isotropic states, in the sense that the variance of the anisotropies, both the variance and the mean value have a confined and an oscillatory character, also arbitrarily close to the bouncing point that in this picture occurs for tau equal to 0. So basically, if we start with eigenstates with small anisotropies, we're able to maintain the anisotropy small along the dynamics. And in order to enforce this result, we have also investigated the quantum behavior of share, that is a quantity that accounts for the anisotropic character of the model. In fact, as you can see here, it is related to the difference between the three Abel parameters computed along the three spatial directions that are anisotropic in this model. And also in this case, both the mean value and the variance show a confined and an oscillatory character in time, also arbitrarily close to the bouncing point that is tau equal to 0. So the analysis so far has demonstrated that the presence together of the harmonic potential and of the polymer effects are able to regularize the quantum behavior of the anisotropies. In particular, the presence of the harmonic potential is a necessary condition to maintain the universe in a quasi-isotropic state. In fact, if we neglect the potential in the Schrödinger equation, we end up basically with the equation for a free particle that corresponds to taking consideration the Bianchi-1 model, that is the simplest anisotropic Vastil homogeneous model. And in this case, by neglecting the potential, we have that polymer effects cannot affect the quantum behavior of the anisotropies, since we have not a time-dependent frequency anymore, we have not an harmonic oscillator anymore. So as you can see from this plot, the wave function for the anisotropies delocalizes along the dynamics, and the divergence of the anisotropies and both of the mean value and the variance is not prevented anymore, as you can see from the dynamics of the peak and from the width of the wave functions. So in the Bianchi-1 model, the anisotropies are not under control across the big bounds. But is it also sufficient condition? So with the presence of the harmonic potential is sufficient to maintain the universe in a quasi-isotropic state? The answer is negative, in the sense that if we consider the Bianchi-9 potential in the dynamics, so we still deal with a harmonic oscillator at a quantum level, but we neglect the polymer effects on the semi-classical background. So basically, if we consider a singular evolution for the universe area instead of a bouncing behavior, we have that the divergence of the anisotropies is not prevented anymore. So the only presence of the potential is not sufficient to maintain the universe localized on the semi-classical trajectory. So to conclude, in our work, we have reformulated the Vilenkin approach in the momentum representation in order to make it compatible with the polymer formulation. We have demonstrated that the polymer formulation is able to regularize the semi-classical background and to replace the initial singularity with a big bounce, and that the Vilenkin approach provides a Schrödinger evolution for the quantum system. And we have also demonstrated that if we start with a very generic cosmological model, such as the Bianchi-9 and we initially suppose that anisotropies are small, we can apply the Vilenkin approach, and we can maintain the universe in this quasi-isotropic state thanks to the presence of the Bianchi-9 potential arbitrarily close to the bouncing point. Thanks for the attention, and that's the link for the paper if you are interested in.
Thank you, Nora. So are there any questions for our speaker? Let me check it. Online.
Hi, I have a question. Can you hear me?
Yes.
Yes.
Okay. Hi, Leonardo. Thank you for the nice talk. I was wondering, when you showed the amplitude associated to the shear and the anisotropies, you had the plot with different oscillatory behaviors. I was wondering if you could comment on the values that you obtained to show these plots, and if there is, for example, some specific values where you can obtain an almost flat oscillation, or for example, the most extreme, let's say, oscillation in these plots.
Okay, thanks for the question. Different colors relates to different energy levels. So basically, the strongest oscillatory character corresponds to the highest energy level. So if you are in the lowest energy level, that is the blue one, you have more flat behavior. That's the difference between the dynamics here.
Oh, okay. So you have, let's say, a clear first, let's say, oscillation, and then you can go up and up in energy.
Yeah.
Okay, thanks.
Yeah, thanks for the comment. I didn't mention this in the presentation.
Any other question in the audience? No. If not, we should thank again our speaker, Eleonora.
Thank you.
And so we are moving to the last talk of this session, which will be presented by Giulia Maniccia. And you can share your presentation, Giulia.
Hi, thank you. Yes, I'm sharing now.
So she will be presenting her work on gauging gravity fluctuation in the WKB approach. Giulia, when you want.
Okay, is it visible?
Yes.
Okay, perfect. Oops, maybe sorry, I'm trying to make this disappear. Okay, no? Well, it's okay, like this. Okay, sorry. So thank you again and good afternoon. First of all, let me thank the organizers for the opportunity to present my work in this nice conference, which is sadly coming to an end. And I hope I can join in presence for the next editions. As you can see from my slide, I will talk about the possibility to include and take into account the graviton fluctuations in WKB approaches for canonical quantum gravity and matter systems. And this talk is based on this work that you can see here. You can find it also on the archive. If you want, you can contact me. So first of all, let me start with a brief introduction on why we use the so-called WKB approach, and why I will talk also about the recovery of quantum field theory in this picture and the possible inclusion of quantum gravity corrections. So we know that we can represent physics on a scale, and until now we have, let's say, a very good knowledge of some points of this cube. And for example, we have quantum field theory in curved spacetime, which is a very nice theory, and we can use it to describe many phenomenologies. But we also want to arrive at some point to a theory of quantum gravity, which we do not have yet. What we can do is we can start from quantum field theory in curved spacetime and try to go close to the quantum gravity regime, which is expressed by the Planck scale. And this could give us corrections, which could be meaningful to describe some phenomenologies that we describe today with quantum field theory on curved spacetime. For example, we could have some quantum gravity corrections, which are important, possibly for black holes and also for the inflationary era of our universe. So let me just now move to the system of quantum gravity and matter. I will talk about the canonical approach. And for the canonical quantization, we need an Hamiltonian formulation. So to obtain the Hamiltonian formulation of gravity, we can start from the four-dimensional formalism and perform the so-called Arnold Desser-Misner foliation. So essentially, we identify a time-like direction, and then we foliate with the normal hypersurfaces. We get some new variables to use, which are the components of this so-called deformation vector and mu, and the induced metric, Hij, on these hypersurfaces, from which we can construct, for example, the connection, the scalar curvature, etc. And in these variables, the Hamiltonian takes an important form because it is clearly related to some constraints. So this is the form of the Hamiltonian, and here we have some momenta, pi and pi k, related to the components of the deformation vector. And we have this function h and hi, which are called super-Hamiltonian and super-momentum. And if we look at the constraints that emerge during this computation, we have that due to the primary constraints, the first two terms must be equal to 0. And due to the secondary ones, the second two must also be equal to 0. This means that the total Hamiltonian up to border term is vanishing. And so in the canonical quantization scheme, the one implemented by Dirac, we have that essentially our wave function is not evolving in time. But for now, I've been talking about gravity. So what happens if we consider gravity and matter together in this picture? So we have a wave function, which can be expressed in this way, and considering some scalar matter fields. The dynamics is described by the so-called Wheeler-DeWitt equation, which is this super-Hamiltonian constraint. As you can see here, again, there is no time operator, but this issue, let's say, is referred to frozen formalism and can be overcome by introducing a time. This can be done in many ways. For example, the time before quantization approach, where we first identify time and then we quantize everything, or the time after quantization, where the whole equation is quantized and then the time is implemented, or relational approaches where essentially the relation between observables is used as a clock. I will focus here on the second approach, which is the time after quantization. So now let me move on to the WKB picture. I'm here considering a system of gravity and matter. The first thing that we can do is perform a sort of Born-Oppenheimer separation, since we are considering that gravity is at a higher scale with respect to matter. And then we can perform this so-called WKB expansion, which takes the name from Wenzel, Kramer, and Brillouin, in some chosen parameter. Here we have a Planckian parameter, which is related to the Planck mass. Essentially, it works in this way. We take a wave function and we perform this factorization due to the Born-Oppenheimer, let's say, separation. So we have a slow quantum gravity term and a fast quantum matter sector. And each of these terms is written in an exponential form, where the exponent is given by an infinite series driven by this perturbation parameter. This approach is very powerful because as it has been shown in literature, it can give us many things at once just by taking this wave function and plugging it inside the constraints. So order by order, we get the classical limit for gravity. Then we get the QFT on curved space-time limit when we define time in this way that you can see here on the slide. So essentially, we say that the matter sector has a dependence on the slow gravitational variables, and we use that dependence to construct a time. So we get a functional Schrödinger dynamics. And then we can also go to the next order, where we get some corrections to such dynamics, which are attributed to the quantum nature of gravity. However, there has been some discussions on if these terms are unitary or not. Let me just do some remarks on this approach. So first of all, the time implementation that I showed you before indeed allows to write a Schrödinger equation for matter, but we have to consider that actually these variables here, the HA variables, they are the same variables of the induced matrix, but I'm working in a mini superspace model. They are not actually completely classical. They have small fluctuations because we are in a WKB picture. And so if we are implementing time in this way, we are not really reconstructing QFT on curved space-time. Also, if we require any condition on the gravitational part of the wave function a priori, as it has been done, for example, in literature, in the works by Vilenkin, we are actually breaking a gauge symmetry, which is related to the Born-Oppenheimer separation, which is this space shift that you can see here with the phase depending only on the gravitational slow variables. And if we look at the cosmological picture, this equation is telling us that we have a matter wave function which depends on a quantum gravitational variable, for example, the scale factor. And so if we want to recover some phenomenology, we need to do some sort of average procedure on this wave function. So now I can finally go on to our proposal. So as you can see here, basically summing up what I said before, in the WKB picture, usually time is implemented by the dependence of the fast part on the slow variables. And indeed, the QFT in curved space-time could be introduced the limits and also the quantum gravity corrections, but there was some discussion on the points that I told you before. And to address those points, we wanted to separate the classical background from some small gravitational perturbations, then make use of the gauge symmetry of the Born-Oppenheimer picture and select a specific gauge, and then average over these fluctuations such that we can obtain a matter wave functional, which indeed corresponds to the QFT limit. So essentially, I will show you that we proved this statement that the gravitons degrees of freedom in this picture have an associated gauge, and we can exploit this gauge to recover QFT on curved spacetime as an effective theory. So in our model, we considered a classical background of Bianchi 1 universe, some small perturbations in the form of tensor perturbations, so gravitons, and then a matter field, a matter sector with a single scalar field which plays the role of the inflaton. So our Hamiltonian has these forms. We have some variables alpha and beta plus minus for the Bianchi 1 sector. Then we have the gravitons sector, and then we have the matter one. We consider the quantization of the full Wheeler-DeWitt equation, so the total Hamiltonian constraint, without giving some conditions on the gravitational part only, which, for example, were implemented in Vilenkin's work. Our ansatz is written in this way. So we have a gravitational part, which depends both, let's say, on the classical variables and on the small graviton fluctuations. And then we have the first part, which depends mainly on the matter fields, but possibly also on the other variables. And we consider the WKB expansion up to the order M0, since this is sufficient to prove what we wanted to prove. Working in the conformal time gauge, we actually constructed a time operator which sees only the classical variables, so only the alpha, beta plus, and beta minus variables of the Bianchi 1 sector. Then we found that indeed we can select a gauge associated to the Born-Oppenheimer symmetry. And this gauge here is written for the gravitational part of the wave function. You can see here that we have the function S1, which is the one which sees the gravitons, so the small fluctuations. But you can also write this equation equivalently for the phase theta, if you want. And it is important to notice that in this equation, we have indeed the same time operator that we defined before. So this gauge is actually describing the dynamics of the gravitons perturbations. But we are also interested about what happens to the matter sector. So we can construct an averaged matter wave functional. As you can see here, I'm removing the dependence on the small graviton fluctuations. So let's say the quantum part of the gravitational sector by averaging over the amplitude associated to these gravitons, since here I'm using the function S1. In this way, I'm obtaining a matter wave function which depends obviously on the matter sector and then on the classical gravitational variables. And by making the computation, we found that actually this wave function obeys a Schrödinger equation, which is of functional form, but it is indeed the Schrödinger equation that we expect for the matter fields on curved spacetime. So actually, we are obtaining the QFT on curved spacetime limit in this approach without considering any gravitational constraint a priori. But it is also important to notice that if you look at the equation for the gauge, let me just go back for a moment here, the equation number 2, and you consider, for example, the assumption that Vilenkin had in his work, which was the assumption that this term here was equal to 0, so that in some sense also the super Hamiltonian constraint of gravity alone was satisfied. Actually, the WKB expansion of this condition is equivalent to the gauge we found. So we did not consider this hypothesis from the start, but in our procedure, we have a gauge which is exactly equivalent to this condition. And in this sense, we have justified a posteriori why that assumption was valid in this picture. So just to conclude, I have shown you that the gauge freedom, which is typical of the Born-Oppenheimer separation in this picture, can be used instead of assuming any gravitational constraint from the beginning. Also, that the quantum gravitational component that we wanted to consider emerges as graviton fields, since we considered a vacuum background model. And these figures of freedom indeed have their own dynamics. And then also that the matter evolution can be recovered only after we average over these quantum fluctuations, as in an effective field theory, and we fix their gauge to describe their dynamics. But this work is obviously not completely done because we also want to consider how it is possible to compute the dynamics and perform this gauge selection at the next orders, and if it is possible to read the different time construction that we have in WKB approaches. And that is all. Thank you for the attention.
Thank you, Julia. Thank you, Julia. So, are there any questions? No? Let me check on the online audience. If you want to think about it, I will give you like some time to elaborate.
Or not?
No
I
question?
can hear you like a bit far. I think that's Eleonora's voice.
Finger raised.
Can you hear me well?
Eleonora,
Okay.
please.
Okay, I have just a curiosity.
Mhm.
Are you thinking of extending this work to other Bianchi models? And also, how is relevant the choice of the lapse function here, the conformal timing, if it is possible, how the choice of the time gauge affects the analysis you showed here?
Oh, okay. Thank you for the question. So indeed, we decided to work with the Bianchi one universe because it was more convenient for our computation, but we are actually considering if the same approach could be brought on in the other more general Bianchi models. That is indeed a possibility. We considered the Bianchi one because it is essentially the simplest case with anisotropies, and we were interested also in considering those degrees of freedom. But in the future, we might indeed consider more general Bianchi universes. And regarding the role of the lapse function, well, actually, that always enters the definition of the time in the WKB approach by Vilenkin. So in this case, we considered a mini superspace model with essentially only the lapse function and not the shift vector part of the deformation vector. But the presence of the lapse function is necessary for the time definition. In our case, we considered indeed the conformal time gauge because that is the most convenient gauge to work with the fluctuations, essentially, because it has a gauge invariant formulation for the fluctuations. But in principle, other lapse functions could be implemented also in this way, yes.
Thank you.
Thank you.
So if there are not any more questions, let's thank again our speaker, Julia.
Thank you.
Thank you, Julia. Bye. And so with this talk, this edition of the winter workshop come to its natural end. So thank you to everyone, to the survivors still here at the last session, to the online audience, and to everyone that has contributed to this workshop. And thank you, Flavio, for most of all for the International Football 5 Championship, which took place on Monday, even though the home team lost the match. We have here some of the winners. Congratulations. We will repeat the next year for sure. And so if Flavio wants to add some word, no?
See you in Madrid next year.
See you in Madrid next year. Bye.
See you in Madrid.